with this controller is you have the motherboard on the left. So here we're in the actual code base for the Fancontroller, and this is my first video where I show some code. So I'll just show you around. This is Atmel Studio, basically de facto programming environment if you do a lot of stuff with AVR microcontrollers. You can just use any text editor and use the separate compiler software, especially if you're not on Windows, because this is Windows only. This IDE is based on Visual Studio, which is a Windows only. So here on the right, there's the project tree with all the dependency files and that kind of stuff. You can browse around and see all the files that you're using. And here is the output window where you get all your error messages and that kind of stuff. So just in case you're new to this kind of programming, this is such a small program, and there's no need for me to split it up in multiple C files. In general, if you're making open source projects, it's always good to put your licensing and identification information right at the top so people can copy it over if they want to fork it. In this case, this is a Commons project, so I don't care. You can strip out all the comments and all the stuff. And there is a little explanation of how the firmware is laid out, because this is not always obvious from the actual code itself. The code is not, because the code is interrupt driven mostly, it's not always clear what happens. Well, I've got some variables here and some includes, and then bam, we're in the main function. And again, as is customary in most even small embedded projects, it's a good idea for your main function, because this is the program entry point. Your program starts here. It's a good idea to just rip out everything that's about initializing hardware and to rip out everything that's like a big function in a main function. So in this case, I've got hardware initialization and I've got eeprom setting reading, which I broke out. So let's look at those functions. This here function is eeprom initialization. Obviously, you want the Fancontroller to keep its settings. So here I read in the 4 eeprom settings, the minimum and maximum PWM clip values and the minimum and maximum tachometer clipping values. And I put in the setting we're currently on. And then I translate those values. You can look at the code itself. I translate them to something that's easier to work with in the microcontroller itself. And I turn on the LED corresponding to the setting you're currently editing. And then we go through initialize hardware. And again, you'll see this in lots of projects. First thing you do is you make sure that the general purpose IO pins are all configured correctly. So the DDR are the direction registers, which tell the microcontroller that all these pins here are output pins, and the port registers tell which pin has to be on or off. And in this case, these types of microcontrollers also use the port register to do pull-up management. So the up and down buttons, I use the pull-ups that are in the microcontroller and I turn them on with this statement. Then I turn on my interrupts. This is the interrupt that triggers on the fan RPM signal. And this is the interrupt that triggers on the button presses. I turn on timer 0 and timer 1. And then I turn on global interrupts. This statement turns on interrupts, so the microcontroller, when a certain signal is triggered, it goes to the relevant interrupt service routine. All right, so the PWM output here. This block of code configures the timer 1, which outputs the PWM signal to the output pin. So first what I do is I say with this statement, I tell this block of hardware to output its PWM to this specific pin, so that I don't ever have to worry about it again. This timer just runs. Every 1/25,000th of a second, it will output this PWM value to the pin. Specifically, in this statement, I tell it run at 1/8 of the frequency of the microcontroller. And this microcontroller runs at 8 megahertz. So 1/8 of the frequency is 1 megahertz. And then here I have the PWM period. ICR1 contains the period. That's 40 timer ticks. That means that this timer has a frequency of 1 megahertz divided by 40, which is 25 kilohertz. And this contains the duty cycle value, which has to be something between 0 and 40. In this case, I initialize it with 20. So the duty cycle is 50%. It's 20 divided by 40 is 50%. So this block, this configuration information, once the microcontroller has executed this, it has configured this timer to run at this certain frequency and to output this all the time to that pin. And I don't ever have to do anything. I don't have to manually in the code somewhere turn that pin on and off or anything. This is just configured. It will run, it will output, never have to worry about it again. And it's even better. If I want to change the PWM duty cycle, all I have to do is change this to say OCR1A equals some other value. Now there's something else I configure here. I say enable overflow interrupt. And this overflow interrupt triggers a specific piece of code, this piece of code, every time the timer overflows, and that is every 25 thousandths of a second. So this interrupt service routine runs 25,000 times per second. And what this does is it increments a value, the variable called tach. And if this value reaches a certain value, namely tach period, it outputs a pulse to the tachometer signal going to the motherboard. So this uses a subdivision. Every n PWM cycles, it will output a tachometer pulse output. These two signals are related to each other by this multiplier, or actually by this multiplier. And this enables me to use one timer for 2 timed signals. Now the nice thing here, even though this piece of code runs 25,000 times per second, which is a lot, even for such a microcontroller, this is kind of a high load to bear. Most of the time, all it has to do is this, increment one value and then evaluate this, and this evaluates to false. So it has 2 fairly easy statements to process. And that means that this interrupt service routine is very quick to execute, and it won't cause any problems. Now, if you would have a really big piece of code here that does all kinds of checks, and you run that 25,000 times per second, your microcontroller can seem like it has just locked up. So that's something to keep in mind, that you don't use interrupts too quickly. All right, so we're incrementing this value last tach, and this value is incremented every time a tachometer output signal is flipped. And we're using this because we are also detecting tachometer pulses from the fan itself. And every time that runs, or every time a tachometer pulse is sensed, this interrupt service routine, the pin change interrupt 0, executed. So this, like every half revolution of the fan, this is triggered. So that's like 100 to 1,000 times per second. And what this does is, ideally this board has to output exactly as many tachometer signals as it gets from the fan, because you want the actual fan speed to be relayed from the fan to the motherboard. So when this ISR is triggered, you expect that since the last time it was triggered, we have outputted 1 pulse. So that's what it's checked. That's what it's checking. If no pulses have been sent out since the last time this triggered, then obviously we are not outputting enough. So we need to reduce the tachometer period. Except, of course, if we are at the limits, if we're clipping. So say a fan is running at 30,000 RPM, but you have configured the fan controller to limit the maximum RPM that the motherboard gets to 5,000 RPM. Well, then it's like, I don't care, man, or this value is at its limit, so I'm not going to execute this period reduction. And in the same vein, if we actually output more pulses per second, we're going to try to increase the tachometer period to slow down the signal. And then it resets the last tach value at the end of this interrupt. And then lastly, we have this interrupt service routine, which triggers on the button presses. So if you press a button, the interrupt service routine will check which button you pressed and then set a certain variable called button pressed. And then this stops. For the same reason, like I could put all the code here to handle the button presses, so to increase or decrease a certain setting. But that would be kind of annoying. This small interrupt service routine will choke out all the others and we'll get glitches. So really we want to keep this as short as possible and do the rest in the main loop, because the main loop is interruptible. So let's go there. So basically this, just to go back to this is all we need to do the tachometer signal. So the tachometer input and output, it's all done here and here for the output. We have the PWM output just running all the time in hardware. We don't have to do any code for that. We output the tachometer signal in this timer overflow interrupt. We sense it. We sense the tachometer input in this interrupt. And if necessary, we modify the output signal. And we have the buttons. So the only thing we have to do now is handle the button presses. So if a button is pressed, we want to make sure we do the appropriate action. And we have to measure the PWM duty cycle that the motherboard is sending to the fan, and if necessary, change that. So let's go to the main loop. So here we're at the main loop. Just put in an enter here. This while one loop always runs unless an interrupt flag is raised. So all this code here is continuously running. First of all, we have if button pressed. So if a button was pressed, we look at whether the button was the up or the down button that was pressed, and then we do the appropriate action. So we change a variable called eeprom settings, and then we change a variable called fizz settings. I won't go into this exactly what this is doing, but this enables me to have kind of simple. The eeprom settings are just a number from 0 to 20 that relates to some other number that's actually used by the code. So this is just like a translation step. You can look in the code yourself to see how it exactly works. And then at the end of button pressed, I say button press is 0, so that a new button press can be serviced. Because if the button press is not 0, this whole routine will check if there's already a button press that has not been serviced yet. So it won't be able to process any new button presses. So I have to do that. And besides the button presses, the only other thing we have to do is measure PWM. And that's what we do here. First, we wait for a leading edge. So we wait for the PWM input from the motherboard to go from low to high. And we just wait a while. And we make sure using this variable, again, you can look in the code yourself. We make sure that we don't wait infinitely long, like we don't wait for seconds. At most, we wait for like 1 or 2 milliseconds or something. Because if a leading edge doesn't come around in 1 or 2 milliseconds, we know pretty sure that there is no PWM signal. So this is important because otherwise you will always, if you don't account for these situations where nothing actually happens, where this will never be true, then there is a very good chance that you will lock up this whole loop and it will never be able to surface, for instance, a button press, because the code will never go beyond this point. And after it has a leading edge, it waits for a falling edge, again with the same kind of deal, and then it measures the PWM duty cycle by reading timer counter 0, which here it is reset, and then it waits, and then it reads the value of how much time has passed since this line went high, e.g. It measures the PWM duty cycle. And then if we actually measured something and it didn't time out, we store this new duty cycle value in the OCR1A, in the compare value for the PWM, and we're done. So this is all the code that runs on the Fancontroller. You can look it up on GitHub and try it out for yourself. So here we're in the actual code base for the Fancontroller, and this is my first video where I show some code. So I'll just show you around. This is not script. This is the de facto programming environment if you do a lot of stuff with you can just use any